Okay, everybody, we're gonna get underway. So this evening we're looking at ideas within chapter 4. Last time we began the chapter by considering some general properties of aqueous solutions. Aqueous, we learned that means that we're dissolving things within water. Water is the solvent and the things we dissolve in it are solutes. So when we were looking at characterizing the solutes that we added or could add, last time we addressed ones that might be considered strong electrolytes or non-electrolytes. And when we classified them, we found a pattern. We found that we had examples of non-electrolytes when the solute consisted of molecules that were added and they remained as molecules. Sugar was an example. I suggested a few other ones. And we had examples that were strong electrolytes. And thus far, we characterized ionic compounds as being strong electrolytes. When we added those to the water, ions were produced. We didn't find any molecules. And we didn't have any examples of weak electrolytes, but we will this evening. We also spent some time looking then at oxidation reduction reactions. We had 3 specific skills. We wanted to be able to assign oxidation numbers. We wanted to be able to identify and describe redox reactions. And that begins by assigning the oxidation numbers and determining the species that was reduced and the one that was oxidized. So we had that particular objective, and then we used the activity series to be able to predict whether a redox reaction would take place. So this evening now we're going to add to that, and we're going to be looking at 3 different sets of ideas. We're going to spend some time looking at solubility and precipitation, some time with acids and bases, and closing with looking at the concentration of solutions. So some of these ideas are from our pre-class videos, and other ones are going to be new this evening. I thought people have been doing a really great job in perusal on getting a head start on these, and that's going to be especially important this evening. The kinds of skills that we're going to seek to be able to master, we want to be able to describe the concentration of solutions and do calculations on that, look at precipitation reactions, characterize things as strong and weak acids and bases, and consider what takes place in an acid-base neutralization reaction. So let's get rolling. So in section 4.2, that's where we're looking at different types of precipitation reactions. 3 different topics there. We want to understand what are called solubility guidelines. We want to use that to predict whether we have a precipitation reaction, which is an exchange reaction. And we want to be able to write what are called ionic equations and identify spectator ions. These are all skills in 4.2. So let's connect this to what we were thinking about last time. So last time we said that ionic compounds, to the extent that they dissolve, are going to produce ions. No molecules are present when an ionic compound dissolves. And we were trying to think about this in terms of, well, what's in the beaker? So take a second here. If solid sodium chloride is added to water, what would you say is in the beaker? How about solid strontium phosphate? Now, strontium phosphate, I show where strontium is on the periodic table. So take a second, think for yourself. What do you think's in the beaker when we add sodium chloride to water? What's in the beaker when we dissolve the strontium phosphate in water? Now, I think out of these 2, you're going to have a much better, it might be much easier, much quicker for you to say, okay, sodium chloride, NaCl aqueous, and to think about how that dissociates. And the reason I say it's easier, for the strontium phosphate, you got to work a little bit harder to think about, well, strontium's an alkaline earth. It's going to be +2. Phosphate's PO4 3-, so I've got to come up with an equation for that. Both of these are ionic compounds, but I think you got to work a little bit harder to get the formula for the strontium phosphate. Let's look and see what happens when these are added to water. So here's a PhET sim for that. So I'm going to start with the sodium chloride. I add the sodium chloride, and we see it dissociates. On the right-hand side here, it tells you the particles that are present. We see that when sodium chloride dissolves, we have an equal number of sodium ions and chloride anions. I can keep adding it, and it keeps dissolving. Now, can I dissolve an infinite amount? I mean, is it like a black hole? Can you keep dissolving it? I'm adding more and more sodium chloride. Okay, now I've got sort of a chunk of sodium chloride and it looks like it's going and it's going to settle at the bottom. It's telling me that I have both dissolved sodium chloride and some of it bound together as an ionic compound there. If I add even more sodium chloride, doesn't look like I'm changing the amount that's dissolved. I see this back and forth between it being dissolved and being the ionic compound. This is a great description of equilibrium. This back and forth, and this is what's making what's called a saturated solution. We've maximized the amount of sodium chloride that can dissolve in the water. Now for the strontium phosphate, we can also see how that dissociates. Notice that it's not in a 1-to-1 ratio because the empirical formula wasn't 1-to-1. It was 3 cations for every 2 polyatomic anions. Strontium phosphate here is dissolving. Okay, now it looks like I've reached the maximum amount for the strontium phosphate. And I reached this a lot sooner than I did with the sodium chloride. I think they're both ionic compounds. They're both dissociating to give me ions, but the maximum number of ions they could produce in the solution is quite different. I think that the sodium chloride is more soluble, more of it can dissolve than the strontium phosphate. So when I say that we have ionic compounds, when they dissolve, produce ions, not molecules, that's our description for a strong electrolyte. But this doesn't mean that every strong electrolyte is going to be highly soluble in water. Sodium chloride, I can get a lot of ions to dissolve. Strontium phosphate, far fewer before it makes what's called its saturated solution, and I reach the maximum amount. So when I'm comparing these different ionic compounds, I'd say in both cases, there's strong electrolytes that are breaking apart to give me ions. I don't have any molecules present, but there are differences in terms of how soluble they are. Those differences in how soluble they are, even though they're ionic compounds, is shown here in this data table right here. This is provided information that you'll have to use on your next test. So last time we mentioned one type of provided information. That was the activity series. Here's another table that we want to understand how to use. These are solubility guidelines for various ionic compounds. So let's look at the details on this. So it's listed here at the top. These are compounds that are quite soluble, and they're listed based on what the anion is. So compounds containing these anions are typically quite soluble. A lot of them would dissolve, a lot of it would dissolve in water. Below, we've got examples that are not very soluble, again, based on the anions. And then on the right-hand side here, these are exceptions to that. These are exceptions, meaning, okay, chlorides are almost always quite soluble unless they're found with these cations. Or at the bottom, sulfides are quite insoluble unless they're found with these. That's what it means to say that there are exceptions. The exceptions are going to be important because they will be a guide that tells us whether or not we have a precipitation reaction. Let me show you what I mean. So let's say we take lead nitrate and we add it to water. We take potassium iodide, we add it to another beaker of water. So our first question is, well, what's going to be in the beaker? So in both cases, I'm going to look to see what do I know about their solubility. I have lead nitrate. All nitrates are quite soluble, so it will break apart and give me the cations and the anions. Potassium iodide, I'm going to look at iodides. Iodides are quite soluble. There are a few exceptions, but not potassium. So I'd say in the beaker, this is what would be present in each of those beakers. That's how I'm interpreting the provided data. So what happens if I mix them together? So this is showing a figure from your book. In the top beaker, they had the potassium iodide with those ions separate and floating around. In the bottom is the lead nitrate. Those ions separate and floating around. When you mix them together, this is a cool demonstration. I mean, it's almost like magic. You got these two clear solutions. When you put it together, You see this yellow solid form. If I could go back in time and be a magician and wow, I don't know, people in the Middle Ages, this would be the demonstration I would use. It's remarkable. Two clear solutions, you put it together and it gives you this brilliant yellow. That brilliant yellow is the lead iodide being formed. And you still then have the potassium nitrate floating around in the solution. So the way that we could use the table to predict this, we saw what was going to be in the two beakers. And now we could consider, well, do we have a combination that leads to a precipitate? Lead and nitrate was in the beaker as ions. Potassium and iodide were in beaker as ions. So let's look at the different combinations. How about the potassium combining with the nitrate? Nope, doesn't look like that gives me a precipitate. All nitrates are soluble. How about the other combination? Aha, this is where the precipitate's forming. The solid ends up forming. Because even though iodides are soluble, an exception is when it's combining with the lead. So those exceptions, those are what give rise to when we can have precipitation reactions take place. That's how we use this table to predict whether we have a precipitation reaction take place or whether the ions are still just floating in the beaker. So this would be the description for what took place. And this is what we show with the image below. Lead nitrate solution is combining with a potassium iodide solution to form lead iodide and potassium nitrate. When it says the solid part, that's the precipitate that's forming. And when it says aqueous, those are the ions that are floating around in the beaker. So this whole description right here, this is called the molecular equation. Let me now show you something with that. So at the top, that was the entire molecular equation. We're going to turn that into what's called the full ionic equation. When we break it apart into the full ionic equation, what we're going to do is all of the aqueous strong electrolytes, we're going to break them apart. Lead nitrate aqueous is really lead ions and nitrate ions. So let's write them separate from each other. Potassium iodide aqueous is really potassium ions and iodide ions. So let's write them apart from each other. So it's really this idea of let's write what's in the beaker. This is what was floating around in each of the beakers. I am breaking apart the aqueous strong electrolytes. Lead iodide solid, well, that's not aqueous. That's a solid, so I'm not going to break that apart. But potassium nitrate aqueous, I'm going to break that apart into its component parts. So this would be the full ionic equation of everything that's involved. Then the next thing that we do is we'll still have the solid that we have there being formed. But with our other features right here, we can look to see, do we have something on both the left-hand side and the right-hand side, both before the reaction and afterwards? If it is present both before and after, we can think about canceling it. And by canceling it, I mean, it's not very interesting. It was floating around in the beaker beforehand. It's floating around in the beaker afterwards. It wasn't involved in the reaction. If we cancel out the things that were just floating around in the beaker both before and after, we find that we're left with what's called the net ionic equation. So the core of what happened here, the interesting chemistry on this was we had lead 2+ ions combining with the iodide ions to form lead iodide. That was the solid that formed. Now, when I say floating around in the beaker both before and after, if something's floating around in the beaker both before and after and we're canceling it, those are called spectator ions. I like that name. Spectator, they're just watching the reaction that took place. So what we've done within here, several different skills. We had an initial reaction that we looked at the solubility guidelines to determine whether a precipitate would form. We wrote that particular reaction. Next thing that we did was we wrote the entire net ionic equation, the full ionic equation, everything that was present. From that, we could look at a subset of that and say, well, what's the interest in chemistry? That was the net ionic equation. And the species that were just watching along the way, floating in the beaker beforehand and afterwards, not part of the chemistry, those were called the spectator ions. Those are what we ended up canceling out in order to get the net ionic. Let me work through another example for you here. Sodium nitrate and potassium sulfate. Initially, all nitrates are soluble, so sodium nitrate will definitely break apart. Sulfates are quite soluble, and especially with potassium, okay, that's not an exception. So initially, this is what's in the beakers. Now, is there a combination that will lead to a precipitate? Well, I can sort of look at the opposites. Sodium with sulfate, potassium with nitrate, those are all still soluble too. There's no precipitation reaction that takes place here. If I combine both of the solutions, I just have ions floating in there in the combined beaker. No reaction takes place. How about these other examples? Sodium hydroxide and potassium chloride. Let's first of all make sense of how they could initially dissociate. Sodium hydroxide, it says hydroxides are usually insoluble, but wait a minute, an important exception is when I have alkali metals. That's what sodium is. Okay, that explains why sodium hydroxide would be floating in the beaker. Potassium chloride, chlorides are soluble. Okay, so that would be floating in the beaker. Now, in the new combinations then, no reaction takes place because when I switch them, they're still soluble. Potassium combined with hydroxide, that would again be soluble. Sodium combined with chloride, that it would again be soluble. So there's no precipitation reaction taking place there. Take a second, look at this last example. Silver nitrate is combined with ammonium iodide. Look at that, see if you can look at the provided information and determine what precipitate forms, if any. But I'm looking at the combinations of what could be there. Well, I guess I could have something with the silver with the iodide and the ammonium with the nitrate. In both cases, I'm looking to say, what would be the cation and what would be the anion if these were to come together and lead to something with poor solubility? If I look at these different combinations, well, all nitrates are soluble. So ammonium nitrate, that'll still be soluble. That can't be a precipitate. How about the other combination? Silver and iodide. Iodides are usually soluble. Oh, but I see an exception right here. The silver is an exception. Silver iodide then would be a precipitate that would form. The net ionic of the part that would be interesting is then the silver ions are combining with the iodide ions to form silver iodide solid. The ions that are floating around in the beaker both before and after, that would be the ammonium, and that would be the nitrate. So as I've gone through this part, I know I went through it quickly, but I think this is a skill you can put together with just a little bit of practice. What I grabbed right here is, this is the description within the e-text. It really parallels what I was trying to just share with you. I like within the e-text here because it gives you a discussion of what's going on. It gives you a question to try. It gives you the same strategy that I just mentioned. It gives you a sample problem that it works through paired with a video. A problem you can try, another problem, another problem, another problem, another problem. So my point is within here, I know I went quickly through that part, but I really just paralleled the same treatment that's in the textbook. If this is something that you want to continue to explore and practice, that's exactly the first resource that I would then look to. So this is a typical end of chapter question. Will precipitation occur when the following solutions are mixed? If so, write a balanced equation for the reaction. So what you would be doing on this is you would look at the provided solubility data and you'd see if you have a combination with poor solubility. If so, you would write the net ionic equation and determine the corresponding spectator ions. If you can do that, you completely understand the idea. So let me shoot you a poll right here on this topic. What can you do within this one? When it comes to these precipitation ones, what do you feel confident with? Can you identify the question involving solubility guidelines? Would you be able to use that to determine if a precipitate forms? Can you write the net ionic equation? And can you identify the spectator ions? Take about 10 more seconds for me. So I like that folks have a lot of confidence as far as being able to identify the required skills, meaning being able to identify that involves solubility guidelines. As soon as I see the word precipitation, I'm thinking, okay, this is about the solubility guidelines. All of the other skills within that of determining whether a precipitate forms, being able to then write the equation, being able to then determine what the corresponding spectator ions are, they all come back to just using that provided table. So please practice that a couple of times. That provided table would be exactly what you need to try this question here, 4.23. Now, I notice when I look at the end of chapter, this is a really typical way the questions are asked. And a lot of times they're also posed as scenarios. Because what we're doing, after all, we're mixing things and we have a precipitate that forms. So a lot of times that I see these questions written as sort of like lab scenarios. You're trying to separate something or you're trying to add things in different order. Give those a try, okay? So these are, I think, good suggested end of chapter problems. And if you have questions on this, shoot me a message. I'll be happy to help on this one. So this was looking within the section here on precipitation reactions. Our objectives for this are quite clear. We want to be able to apply the solubility rules to predict whether a precipitation reaction occurs. We want to be able to describe that with the net ionic equation, and that includes identification of the spectator ions. Those are our objectives for using this section on precipitation reactions. Moving on to one that was within the pre-class video, that was one topic involving acids and bases. So one thing we want to be able to do is describe acids and bases as being strong or weak. These terms strong or weak, it connects right back to the kinds of electrolytes that we were talking about last time. Last time we talked about things being strong electrolytes or non-electrolytes, but we didn't have example for weak ones. We will tonight. We want to be able to take those acids and bases and then see what happens when they combine, when they react with each other in what's called a neutralization reaction. So we want to be able to write neutralization reactions for these and also describe the corresponding net ionic equations. So in some ways, it's related to the topics that we looked at last time with electrolytes, and it's also related to what we just talked about with precipitation reactions, meaning what is the net ionic equation? So within chapter 4, you see a lot of the ideas become grouped together. So when I'm looking at this idea of strong and weak acids and bases and neutralization reactions, those are going to lead to what I would say the most difficult part of the chapter, which are titrations. But in order to do well with those, we need a solid foundation on these other ideas. So let's explore those now. So I want to take the same ideas that were in the pre-class video, but I'm going to look at them a little bit differently. The comments and questions that folks had within that was really helpful for me to understand your strengths and weaknesses. So let me see if I can improve on a couple of those. So I think when it comes to acids and bases, we want to know, well, what are acids and bases? What do they do in water? How do I identify acids and bases? And what are reactions involving acids and bases? So that first one, what are acids and bases? In water, acids are substances that produce H+. Bases are substances that produce the hydroxide, OH-. So that's our definition. If something produces H+ in the solution, it's an acid. If something produces the hydroxide, OH-, it's a base. That's going to be our description for what are acids and bases. Next thought, how do I identify them? Let me list a whole bunch of acids for you here, and let's try to make sense of this. All of these are acids, and I give at the bottom ... meaning there are many more acids in the world. How do I begin to make sense of this? So first of all of these are molecular substances. In all of these cases, I only see nonmetals. I see elements like hydrogen, nitrogen, oxygen, sulfur, chlorine, fluorine. These are all nonmetals from the right-hand side of the periodic table with hydrogen there too. Second thought is, if I look at all of these, the formula is indicating the number of H pluses that each molecule can contribute to the solution. Look at all of those equations right there. Every single one except for the acetic acid, it starts with the H in the front. And it's telling me how many H plus, how many protons that it can donate to the solution. The only one that doesn't list it that way is acetic acid, because it's trying to show you the connectivity, the structure for that. So this is a really important idea when we're looking at our acids. The formula is telling me how many H pluses they can donate to the solution. Next thought within here, I've grouped them this way. All of the ones at the top there, those are all strong acids. And by strong acids, we can consider them to be strong electrolytes. When they're added to water, no molecules, they're just going to give me ions. That's what a strong electrolyte does. At the bottom here, these are all weak acids. They are weak electrolytes. How do I make sense out of all of these? The easiest strategy, memorize the strong acids. Look how many I have there. 1, 2, 3, 4, 5, 6, 7 strong acids. How many weak acids are there? Hundreds and hundreds and hundreds of them. The easiest strategy, let's memorize the strong ones. And anytime we have an acid, it's either going to be strong or weak. If we memorize, I guess we got two choices. Do you want to memorize the 7 strong acids and then say everything else is weak? Or do you want to memorize the 100,000 weak acids and then say, oh, the other ones must be strong? It's obvious. Let's memorize the strong acids, and then any other acid that we encounter is going to be a weak acid. And a real giveaway that something's an acid, it has this leading hydrogen within the formula. Now, I've listed sort of in larger font here at the bottom 3 weak acids that I want to make sure that you draw your attention to. Acetic acid is a very common weak acid that you're going to see within the book. HF, another very common weak acid. H3PO4, phosphoric acid, another very common weak acid. So make sure that you recognize those in particular as being weak acids, because they are used in many different examples. And these terms, strong electrolytes, weak electrolytes, now we have things within those categories as they pertain to acids. So if I go back to this slide right here, this is what we were working on last time. Let's see how that now applies for images like this. Last time, you did a really good job of identifying things based on the particle description, if it was a strong electrolyte with just ions, non-electrolyte, just molecules, or a weak electrolyte where you had a combination. If I take this now and I think about those different acids, examples of strong electrolytes, I listed the strong acids right there. Those would be examples of strong electrolytes. When I add those, they're going to dissociate and they're going to give me ions. For the weak electrolytes, I've listed that whole group. Those would be ones that when I put them into the water, they're going to give me a combination of ions and molecules. So as an example, if I take nitric acid, strong acid, I put it in water, it dissociates and it just gives me ions. Hydrochloric acid, I put it in water, it dissociates, it just gives me ions. That's our definition for a strong electrolyte. But now we've got examples of weak electrolytes. We said HF was an example of a weak electrolyte. When I put that in water, I get a combination of the molecule and the ions present. That's what it's showing in this picture right here. Molecules and ions present at the same time. That's what will happen with HF. And that's what these back and forth arrows are designating. Acetic acid, weak acid, weak electrolyte. I have a combination of the molecule and the ions present. That's our description for what happens when we have a weak electrolyte. The back and forth arrows, those are designating equilibrium. That's a really big idea in the second semester, not so much in this semester. But right now, if you wanted to say all of the examples of weak electrolytes are ones that are exhibiting this equilibrium behavior, that would be correct. Now, the book designates one other one it draws our attention to, which is what happens with sulfuric acid. It says, although sulfuric acid is a strong electrolyte, it's only the first ionization, only losing the first proton, in which I would draw the arrow going in just one direction. After that, I have an equilibrium that's being set up. So what it's saying is for sulfuric acid, it's a strong acid in terms of losing the first proton. And then after that, I have this combination and it's set up in equilibrium. Not a really important detail for us, but it was mentioned in the book and I wanted to illustrate what that point was talking about. So that was, how do I identify acids and begin thinking about them? How about the bases? So here I list strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. And I'm including the periodic table because look where they're found. All of these are including alkali and alkaline earth hydroxides. Those are what are leading to these strong bases. In a way, we've already sort of been memorizing this. We've already made sense of how an ionic compound is a strong electrolyte. Now we are just saying, oh, it's a base if it is an ionic compound, including these hydroxides here, but it's the same behavior that we would have looked at last time. And when I say the same behavior, we look to see how do things like sodium hydroxide, calcium hydroxide, strontium hydroxide, we looked at how they dissociate. Sodium hydroxide gives me sodium ions in the hydroxide. Calcium hydroxide would give me calcium and 2 hydroxides. Strontium hydroxide would give me strontium and 2 hydroxides. So in some ways, the idea of ionic compounds as being bases, it's pretty close to what we were talking about last time. It's pretty close, with the distinction being that the polyatomic that we're looking at now is the hydroxide group. And when it's added to water, when it dissociates, it produces hydroxide in the solution. And that was our definition for what a base was. These are our examples of our strong bases. One more step within here. And I'm filling up that slide and then I'm going to tell you what I'm up to. This whole group right here, these are all examples of weak bases. And just like with the acids, let's know the examples for the strong ones, and the periodic table can help with that. Then everything else is weak. So if I'm trying to make sense of these weak bases, I'm seeing molecular compounds. Oftentimes I'm seeing nitrogen within the formula. These are all weak bases. They're all weak electrolytes. Now, one thing within this, notice I don't see any hydroxide group in the formula. I saw the hydroxides when I was looking at the ionic compounds. I don't see any hydroxides within the formula. With my weak base, what happens is the base reacts with the water, and that produces the hydroxide. Let me show you what I mean within that. So let's say we take ammonia, NH3. Ammonia can combine with water, the H2O, and what it leads to is then the ammonium cation and the hydroxide. That's what's in equilibrium there. NH3 is combining with H2O. It takes one of the protons from the H2O and becomes NH4 plus, and it then leaves the hydroxide within the water. That's within the solution. That's why I say that these weak bases are weak electrolytes that react with water to produce the hydroxide. It's not their dissociation that produces it. It's when they're reacting with the water itself. And because they are weak electrolytes, they're set up within these back and forth arrows. Now, what I tried to do within this slide right here, I tried to talk us through and try to make sense of a lot of different equations and a lot of different substances that can now sort of be like a summary slide for you. As far as a summary for how do I make sense of acids and bases, this is my summary. And by that, I mean acids produce H+, bases produce hydroxide. I have examples of strong acids. I view them as being molecular substances. There's strong acids and strong electrolytes. But below that, I've got my examples of weak acids that are weak electrolytes. I said that the best way to memorize or make sense of these, let's memorize the strong ones, and all of the other acids that we ever encounter are going to be weak acids. When we're trying to make sense of the bases, we have examples that are ionic compounds, that are strong bases and strong electrolytes, and that when I look at the cations in there, they're from the left-hand side of the periodic table. Lithium, sodium, potassium, calcium, strontium, stuff like that. Below that, I list now the weak bases. These are often molecular, and I'd be looking for nitrogen being present. Weak bases are weak electrolytes, which means they're once again being set up within that, the example right here. Once more, they're being set up where they're going to be in equilibrium, and they're producing the hydroxide. So if I were to take this then, here's another way that I'm going to end up summarizing this. This is information that we made sense of last time. We had examples of non-electrolytes. We had examples of strong electrolytes. We saw that when we take the strong electrolytes, we saw how they would end up dissociating. Let's add to that now. We have an example of how we have our strong bases being ionic compounds that produce the hydroxide. We also have examples of strong electrolytes that are now molecular ones. Those are strong acids. Nitric acid, HCl, HBr, HI, those are all examples that then they dissociate as, even though they're molecular, they dissociate and they're treated as strong electrolytes. And then the in-between part right here, that's where we can now fill in our examples of things that are weak. Our examples that go there now are weak acids and weak bases. And some really classic ones we want to be alert for. Ammonia, really classic example of a weak base reacting with the water to give me the ammonium and the hydroxide. Important weak acids that we want to know, HF is an example, and acetic acid is another example. All of these I'm drawing with arrows going back and forth to represent the corresponding equilibrium. All of these are examples where mostly molecules are present, but some ions are being produced. This would be another one where I feel like a lot of information is being summarized here. A lot of information that I was trying to lead us to different ways that we can now think about these examples for non, weak, and strong electrolytes and connect them to acids and bases. So this was a picture that we had, a representation that we had within the pre-class assignment. So this one was saying the following diagram represents aqueous solutions of these acids, HX, Y, and Z. They're not showing the water molecules, they're just showing the aspects of these acids. And the question asks you to rank them from strongest to weakest. I thought people were doing a really good job within their analysis here. Here was Reagan and Sam telling me a couple different features on this. But if I read their descriptions here closely, I wasn't sure they were telling me exactly the same thing. So Reagan is saying strongest to weakest. HY would be the strongest, then HZ, and then HX. Why? Because HY dissociated completely. I agree. I don't see any molecules there. And then a description of comparing the other two to how much they dissociated. I'm going to agree within that analysis. I see one of them, HY, I would call as strong because I only have ions present. I would call HX and HZ here weak because I see both molecules and ions present. And then Reagan is saying, well, look closely. Which one is dissociated more than the other one? Now, within Samuel's right here, same ranking says HY is the strongest because it has the most cations and anions, and it's followed by HZ and HX. I think that leads to the same result, but I want to point out something and be careful within this. In this comparison, the way the author set it up, I would say in each case, they began with 8 of the molecules, whether it was HX, HY, or HZ. I think in each case, they started with 8 of them. I got that just by putting back together the parts. And in this way, I think it allows an apples to apples comparison. You've got exactly the same number and you can consider how they dissociated or not. Within that analysis, I'd say it led to one of them being strong, the other 2 being weak, and there were differences within that weakness. In a way, something's either strong or then it's weak to varying degrees. So I'd like you to think for a second. Where would you place this one in terms of the acid strength? I changed the number that we were looking at there. This doesn't have 8 to start with. This just had 2 to start with. How would you begin to think about that? Would you say that it's more like one of these other ones? What do you think? Now, most of the responses I see coming in right here, people are saying, we should call it strong. I agree. Our description for strong is saying no molecules present. No molecules present. So I would say that HQ, it looks as strong as HY. Strong is strong. Strong means no molecules present, completely dissociates. So I would say it has the same strength as HY. So my point within this one is that when we are identifying something as strong, weak, or non-electrolyte, it is the extent to which those particular molecules are giving me ions, staying molecules, or are somewhere in between. I don't need to see 8 of them or 80 of them or 4 of them. I can just look to see if it completely dissociates into ions, it must be strong. Now, within that same one right here, I thought this was a very typical chapter 4 question. It's connecting an idea from the start of the chapter, which was looking at things as strong, weak, or non-electrolytes, and now it's connecting it, in this case, to acids. So I'd like to think about this one as we try to say, well, what might show up on the test? Could you answer this question? Could you do the same thing if it was asking you to interpret sodium hydroxide, ammonia, and calcium hydroxide? Let me send you a polling question on that. So let's say it was the same kind of thing, but it was asking about sodium hydroxide, ammonia, and calcium hydroxide. Could you sketch that? Would you know what to look for on a question? You think you could do that? So as those are coming in, what would I be looking for if I was asked to solve this? I think what I would be doing is I would look for each of these. My first thought is, okay, these are going to be bases. Now, if I classify those, I need to consider, are they strong, weak, or non-electrolytes? And then how will they be dissociated? Those are the kind of things that I'm thinking about. So right now, as far as how folks come down on this, I think we're somewhere maybe like a 3.5. Neutral, that's saying, okay, you might be able to do it. So let's see if we will be thinking about the same features. So if I were looking at each of these, if I have sodium hydroxide, what's coming into my mind? Okay, ionic compound. strong base, strong electrolyte. It's going to completely dissociate into sodium and hydroxides. No molecules present. That's what I'm thinking with sodium hydroxide. NH3, okay, what am I thinking now? Okay, this would be a weak base, a classic weak base. If I'm going to memorize one weak base in the whole world, it's going to be ammonia. What will it do? Okay, it's a weak base, so it is a weak electrolyte. It will give me some ions, but it's mainly going to be molecules. It's mainly going to be NH3 molecules. The ions that would be present, a little bit of ammonium, NH4 plus, and a little bit of hydroxide. But most of it is going to remain NH3 molecules, weak electrolyte and a weak base. And then the last one, calcium hydroxide, I'm back to classifying this as, this is an ionic compound. This is a strong electrolyte. It's going to dissociate, and I'm going to see ions, not molecules. And I'm going to see 2 hydroxides for every 1 calcium 2 plus. Those would be the features that I'd be looking to either recognize within a picture or that I'd be trying to draw. It all comes back to, we've got to be able to correctly identify these as strong, weak, or non-electrolytes, and then think about how they would then show up within the corresponding pictures. Here's another way that I've seen it asked. So instead of trying to connect this to particle pictures, it says which of these, when dissolved, is going to be a strong electrolyte? And in the pre-class video, I've challenged you to even go beyond that. Which would be the strong electrolyte? How about classifying all of them? I noticed that folks initially, a lot of people were having success with this. Jordan's within here saying the only strong electrolyte they find is sodium nitrate. They're identifying that way because it's an ionic compound. Exactly. Sodium nitrate, ionic compound. All ionic compounds are strong electrolytes. Then goes on to say that, okay, ammonia is a weak base. B and C are weak acids. And sucrose is a type of a sugar, which is a non-electrolyte. Veronica within here, I liked within her analysis, came to the same consensus. I know for sure that ammonia is a weak electrolyte because it is a weak base. Hydrofluoric acid is a weak electrolyte, and I like the way that she's drawing attention to. This is the one that tricks a lot of students. That's what I'm trying to point out, because a lot of times HF, people think of it as being strong, but it's an example for a weak one. HF is a weak electrolyte. So I'm agreeing with what the students were saying. These would be then the formulas that I would have go with it. Ammonia is NH3, we're going to see that a lot. Hydrofluoric acids, HF, we're going to see that a lot. Folic acid, I don't think we need to know the formula of that. It says it's an acid, and it's got to be a weak acid because it is not one of the strong ones I've memorized. If you want to know the formula, I guess you could, but soon as it is an acid that is not one of the strong ones, I know that it is a weak one. That was my point on that. Sodium nitrate, I think we should be able to draw the formula for that. Sucrose, that's a type of a sugar. You're not going to have to memorize the formula for sucrose or glucose. That's biochemistry stuff. That's not in this class. Okay. So within here, we've been spending time on identifying what are acids and what are bases and being able to identify them. Now let's see what happens with reactions when an acid is combined with a base. Let's look at this to see if we can see what's taking place and also think about it in terms of the corresponding net ionic equation. So when we combine an acid with a base, these are called neutralization reactions. Here would be a couple examples. So here would be a word description. Hydrochloric acid reacts with sodium hydroxide to produce water and the salt sodium chloride. This would be a formula for what's going on. Hydrochloric acid is HCl, sodium hydroxide is the base. Those are both aqueous solutions. They combine, they're going to give me water and sodium chloride. Sodium chloride, this is probably the formula that you associate with salt, but we see right here that salt right now is actually chemically, it's got a particular definition, description. Salt is produced as a product in a neutralization reaction. And we could see that it can have other formulas too. This is what's taking place. We've got, first of all the ions that I initially have are now as reactants. I see water being formed, and I have the sodium and the chloride. So right here, I wrote the full ionic equation. I broke apart all of the aqueous strong electrolytes. I didn't break apart water as a liquid, but I broke apart all of the aqueous strong electrolytes. Now, if we begin to cancel on this, I'd cancel the chloride from each side, the sodium from each side, and what am I left with? H plus hydroxide to give me H2O. The spectator ions, those are what produced the salt. Sodium chloride, that's what was left over. That was the salt that was produced in this neutralization reaction. My strategy for this, I first wrote the equation with the acid and the base. I balanced it. I broke apart the aqueous strong electrolytes, and then I canceled. Let's see if we can do the same thing with another acid-base neutralization reaction. Nitric acid reacts with calcium hydroxide. That's going to produce water and the salt calcium nitrate. Nitric acid and calcium hydroxide, I think we should know the formulas for those. We should also know calcium nitrate. So take a second, see if you can balance that for me. It might seem complex within the balancing. My first feature on that is I would probably look to balance the nitrates. I see that I have 2 nitrates on the right-hand side, and I have nitrate associated over on this side. So let me try a 2 in front of that. That makes the nitrates balanced. I see that I have 1 calcium. Okay, let me keep 1 calcium hydroxide, and then I finish it off by putting how many waters are there. That would be my strategy for balancing this. This points out that I have 2 of the nitric acids for every 1 of the calcium hydroxides. Now, if I want to come up with the net ionic equation, I could do the same strategy as before. I could write all of the full ionic, break it down to all of the parts as reactants, break apart all of the aqueous strong electrolytes as the product. I could cancel out the spectator ions, and this is what it simplifies down to once again. The spectator ions that I have, those are the ones that then produce the corresponding salt that I have. Calcium nitrate is the salt that I have. It's the spectator ions that are produced when I have my strong acid and strong base combining. So within these, a strong acid combines with a strong base. The cations and anions I have, those are the spectator ions, and those lead to this aqueous salt. The net ionic that I have, and you notice in both cases, it reduced down to H plus hydroxide to produce H2O. That reducing down to H plus hydroxide to give me H2O, that is going to be the net ionic equation whenever you have a strong acid combining with a strong base. One more thought, it's always a good idea to make sure you have balanced equations within this. I find that a lot of times students skip that step. They don't balance the acid and base, and especially when we get to solution stoichiometry and titrations, that's a really big issue for them. Let me give you one more example within this. So this is the third one. We did a strong acid with a strong base, another strong acid with a strong base. This one's different. Acetic acid reacts with sodium hydroxide. It's producing water, and the salt in this case is sodium acetate. Now, the reason why this is different, we don't have a strong acid with a strong base. One of these is weak. Is the acetic acid weak, or is the sodium hydroxide weak? It's the acetic acid. So when we look at this right here, we're going to break apart the aqueous strong electrolytes. Break apart the aqueous strong electrolytes. So Acetic acid, it's aqueous, but it's not a strong electrolyte. So I'm going to just keep it written as is. The sodium hydroxide I'll break apart. The water, it's liquid, it's not aqueous. The sodium acetate I break apart because it's an ionic compound. Let me cancel what's on both sides. The only thing that I see on both sides here is the sodium plus. That's the only spectator ion in this example. Now, it might seem like within this we did something quite different, that this, like, it led us to a very different spot. We only have one spectator ion instead of two like we had before. But the strategy is exactly the same. The system is exactly the same. The system is, let's write the balanced equation to start with. Then let's break apart the aqueous strong electrolytes. Then let's cancel, and we'll see the resulting net ionic equation. That plan worked for both of the cases. I'm pointing out that when you have one of them being weak, whether it's the acid or the base, you don't get it reduced down to H plus hydroxide to give you H2O. One last thought within here. In each of these examples, I'm writing them as an arrow just going in one direction. When we looked at things like acetic acid or HF or ammonia, any of those are in equilibrium and they don't break apart completely when they're just in water. But if I put them into a reaction with either an acid or a base, I put the arrow to show it goes just in one direction. Not a crucial thought for us, but I'm just pointing out sometimes that's a hang up for students. They're unclear when to use the arrows going back and forth in one direction, back and forth in both directions, they're just pointed in one direction. For any of our neutralization reactions, we can just use an arrow pointed in one direction. Now, here's an end of chapter or a practice exercise from within the book. This one asks, what's the net ionic equation when you have aqueous ammonia with nitric acid? So let's pause and think for a second. Aqueous ammonia. Ammonia, I'm thinking to myself, okay, that is a weak base. Nitric acid, that is a strong acid. So to get started on it, this is what I think we're combining. We're combining ammonia, which is a weak base. Nitric acid, strong acid. I'll even give you the product here. It's going to be ammonium nitrate. Aqueous is the product. So if I were to look at this right here, what is our strategy to get the net ionic? We're going to take it, we're going to break apart the aqueous strong electrolytes, and then we'll cancel. This is where I think that takes us. I am breaking apart the aqueous strong electrolytes. If it is a weak electrolyte, I'm going to keep it written as is. Let me send you a polling question on this one then. I think I've got you pretty close to the finish line on this. Which of these then corresponds to the correct net ionic equation? In a sense, what I'm asking is, given this full equation right here, after you cancel it, what are you going to be left with? Take about 20 more seconds on this, please. So sharing results with y'all. So the consensus in here is suggesting D is the best choice. I'm going to agree with you on that. I think that if we have this being our full expression, and again, how did I get to the full expression? I had ammonia reacting with nitric acid to form ammonium nitrate. I then dissociate and break apart the aqueous strong electrolytes. Ammonia, it's aqueous, but it's a weak electrolyte. So I'm just going to keep it listed as is. Nitric acid, strong electrolyte. I'm going to break it apart. Ammonium nitrate is a salt. I'll break it apart into ammonium and then nitrate. I should have had a minus sign there. My bad on that. Now, if I end up canceling, what do I end up canceling? I've got nitrate on each side, so I can cancel that. Looks like that's the only thing I have on both sides. So I agree with you for D. It looks like it's NH3 reacts with H plus to give you the ammonium cation. So I agree with your overall analysis.
Can I ask a question
Yeah, go ahead.
that? So because NH3 is a weak base and it has to be reacted in water, is that why you don't have water in that net ionic equation? Because it's on both sides?
Yeah, if I ended up including the water being present, it really wouldn't add any information. When you say being present on both sides, I agree with that. I could add it sort of here on the left-hand side to see where it's initially combining with it, and then on the right-hand side too. But by listing aqueous, I'm sort of already accounted for that.
Okay.
Okay.
Yeah, thank you.
Yep. One more thought, one more topic I want to begin to introduce. And let me pause and say, folks, outstanding job based on your questions and your contributions and what I'm seeing within the chat. I know I'm going quickly through different features right here. I'm really confident that I know what the skills and what you're going to have to do with these ideas. There are a lot of ideas though, and so you're doing a really great job of sticking with me through the different parts. What I want to do within this one, I want to get started on this last idea of looking at the concentration of solutions. And then we're going to finish off next class by looking at concentration, solution stoichiometry, and also a little bit with then chapter 5. So when I say we're doing chapter 4, a little bit more than a week, that's our best way to try to balance what we're up to. So let's look at then here this idea of concentration of solutions. So within this one, we had a FET sim on this one. And folks did a really good job of both predicting and then analyzing. If we take calcium chloride and dissolve it, this really good idea that we're now familiar with, how it gives me 2 chlorides for every 1 calcium cation. So I think we're getting really skilled at being able to predict how these ionic compounds would dissociate. And when I then added this question about, well, how would the concentration change if we did different things, like adding more water from the top, opening the bottom faucet, or allowing it to evaporate? Really nice job within your analysis. This idea that, okay, I think the concentration would decrease if you add more water to it. Because after all, the concentration involves a ratio of the solute and the solvent. So if we keep the same amount of calcium chloride but add more water, it's going to become more dilute. The concentration would go down. If the water is released from the bottom in the same proportion of the calcium chloride leaves, doesn't change the concentration. And then with evaporation, if the solvent leaves, then we see an increase. Really nice analysis. People are doing a great job with that. And I like the way that within the sim, we could explore that as well. Adding more water, the concentration goes down because we're increasing the solvent. Opening up the spigot, they leave in the same proportions within this, so the concentration didn't change. And then with evaporation, concentration increases because we're losing the solvent, the H2O. Really good predictions, and then checking things out within that. Now, the reason I was setting this one up is that when we start to now talk about concentration and put some numbers on it, a lot of times students just fixate on the numbers without thinking about what it means at the particle level. They don't think about what's in the beaker because they just see numbers and they start to begin to use them. So we're thinking about concentration then as a description of how much of the solute is there relative to the solvent. We want to think about what's taking place in terms of the particles, not just the numbers. And what I find is a really common error is failing to account for the manner in which an electrolyte dissociates. And by that, I mean calcium chloride dissociated and gave me 2 chlorides for every 1 calcium. So before we start racing with numbers, a lot of times we got to think and ask, well, how does this dissociate? Let me show you how this now sets up with a couple questions. So we're going to look at part of section 4.5 and think about the topic of molarity, think about how do we express the concentration, and how can we convert between molarity, moles, and volume. Let's get started on that. So here's the definition for molarity. There's different ways to have units for concentration. In this semester, the only unit for concentration we're going to talk about is molarity. It's given the symbol capital M. The definition of it is moles of the solute divided by 1 liter of solution. So we're talking about moles of a solute per liter of solution for the overall solution. This would be sort of how it would be set up if you wanted to make a solution in the lab. Let's say you're using sodium chloride. You have a certain amount of sodium chloride and you dissolve it in a 500 ml volumetric flask. These are what volumetric flasks are. Okay, with a volumetric flask, they have a line like halfway up the neck. When you fill it up to that amount, you know precisely the volume. So with a volumetric flask, you only measure 1 volume. You'd have an example of measuring 1,000 mils, a 1 liter, because you would fill it up to the line on that, or a 250 or a 50. Here I am saying you used a 500. I gave examples, but there's no 500 there. Let's say that's because you've already grabbed the 500 mil volumetric. Okay, you're holding it. That's why it's not in the picture here. But anyways, this would be the way that you would make it. So you would first add the solid to the bottom of your volumetric, and you would volumetric flask, and you'd add enough water to get up to the line. So the reason I'm mentioning this is a lot of times questions involving these making solutions, they describe them as scenarios when it says a volumetric flask filled to the line, it means you've added up enough so that it is now holding half a liter, 500 milliliters. So we could think about this in different ways. And the questions that you had within perusal, they were very insightful for me. So first of all, how many moles of chloride would be in the flask? Well, I want to begin by saying, how does the sodium chloride dissociate? Sodium chloride dissociates 1 to 1. Strong electrolyte breaks apart into sodium and chloride. Got it. How many moles of chloride would be present? I'm going to look to first ask, well, how many moles of sodium chloride did I add? I took 17.61 grams and I looked at the molar mass to figure out how many moles of sodium chloride I added. And then I'm going to note that, okay, I get 1 chloride for every 1 sodium chloride. So this would be a calculation to tell me how many moles of chloride I have aqueous within the within this volumetric flask. Now this next part, I noticed there were a lot of questions on this. So let's see if we can get this part straight. I'm going to ask, what is the concentration of the sodium chloride solution? How much sodium chloride did I add, and what is the total volume? The total volume is half a liter, 500 mils. I think that I added 0.3013 moles of sodium chloride. So I can now determine its molarity by dividing it by half a liter. Now, the part that people are having questions about, when we describe the solute being present there, we got to be able to think about it in different ways. I would say in this case, I added about 0.3 moles of sodium chloride and dissolved it. That became 0.3 moles of sodium chloride aqueous. When I say sodium chloride aqueous, what I'm thinking in my head is, okay, That also could be thought of as 0.3 moles of sodium and 0.3 moles of chloride. So I can think of sodium chloride aqueous, of conceptualizing it in my head as if it's together, even when it's not together and it's broken apart into its component parts. So I was trying to come up with an analogy on this. Let's say you're driving your bike and you crash it into the lake. And when you crash it into the lake, it falls apart. It falls apart and gives you the bike frame and 2 tires. They all come apart. So we could say, okay, let's consider that to be the solute. How many bikes are in the lake? 1 bike is in the lake. Yeah, it's broken apart, but we put 1 bike into the lake. How many frames are in the lake? 1. How many tires are in the lake? 2. So the question is, do we think about it being all together as our solute, or do we talk about the parts on it? Both of them are ways that we can begin to think about it. Now, I know that analogy is probably weak, but it's best I came up with right beforehand, okay? Let's look at this one right here. What's the molar concentration of the sodium ions when you do this procedure right here? You take 2 moles of sodium sulfate and you put it into a 2-liter volumetric flask. This is how I'd answer this one. First thing I would do is I would say, I want to be clear, how does this dissociate? Sodium sulfate is popping in my head as that is a strong electrolyte. It breaks apart and gives me 2 sodiums and 1 sulfate. So if I'm answering this question, that's where I start with. Then I'm thinking, okay, I started with 2 moles of sodium sulfate. When it now dissociates as a strong electrolyte, how many moles of sodium do I have? How many moles of sulfate do I have? Well, I think I have 4 moles of sodium and 2 moles of sulfate. How do I get that? 2 moles of sodium sulfate, I'm looking at the coefficients then. 2 moles of sodium sulfate, when it dissociates, gives me 4 moles of the sodium ions and 2 moles of the sulfate ions. So I'm going to do that bookkeeping first. I'm going to account for the fact that it's a strong electrolyte, and I'm going to consider how many moles I have of the different ions. Now it's asking, okay, tell me the concentration of the sodium ions. I know that it's 4 moles of the sodium ions. It's in a 2-liter solution. 4 divided by 2, that's a 2 molar solution. If I'm talking about the molarity of the sodium plus. 2.0, capital M for molarity. The key step within this process, for me, and what I see with students having difficulty, you got to start right from the start and say, how does this dissociate? Don't start doing the math. Ask yourself, how does this dissociate? And it dissociated and gave me twice as many sodium ions as I had moles of the initial solute. After that, the math ends up being easy. This question right here, these are end of chapter ones that are related in some ways to that skill that I just had. That very first one, 4.69 part A, I think is exactly on that point that I just raised. Which of these will have the highest concentration of potassium ion? 0.2 molar KCl, 0.15 molar of the K2CrO4, 0.080 molar of the potassium phosphate. In each of these, in order to answer it, I first have to ask, how does it dissociate? How does it dissociate? That's another way of saying, what's in the beaker? If I look at these, all of these are ionic compounds. All of these are strong electrolytes. KCl dissociates into potassium and chloride. In the other 2 cases, in the other 2 cases, I have a polyatomic. But this is how each of them dissociate. Before I can answer it, I have to figure out how do they dissociate. The initial concentration for each of them was 0.20 molar KCl, 0.15 molar K2CrO4, or 0.080 molar potassium phosphate. See if you can analyze this for me. How many potassium ions do I get in each case? See if you can analyze that for me and determine which one has the highest concentration of potassium ion and which one has the least. It comes down to how they end up dissociating. When I look at the first one with the KCl, it looks like I get 1 potassium ion for every 1 KCl. So I think in that first case, the concentration would be 0.20 molar potassium, 0.20 molar chloride. How about with the second one right there? 0.15, I've got to double it because I get 2 potassiums for every 1 of the initial solute. For the potassium phosphate, I got to triple the initial because I get 3 potassiums for every 1 of the initial. Okay, now I could end up figuring out which one has the highest concentration. It looks like I have an example here of 0.30 molar for the middle case, 0.24 and 0.20. This one right here, really typical exam question, because what did it require you to do? It required you to classify each of these as, first of all, ionic compounds. It required you to then say, oh, ionic compounds are going to be strong electrolytes. I'm going to dissociate those. And I'm also going to recognize that I have examples with polyatomic anions. So when I dissociate those, I first got to be able to write the expressions to show how they dissociate. And then I had to account for that to determine something like the amount of potassium there. A lot of different features being brought together. This next one is a little bit different. Instead of talking about the concentration, it's talking about the number of moles that you have. Let's pick that up next time. I think you've done an outstanding job hanging with me within the different parts. Let's pick up on that idea and connect it with the very last idea in the chapter, which is solution stoichiometry and titrations. And also, as time allows, we might start a little bit with chapter 5. Now, within here, let me jump down. I want to share one piece of information with you. We mentioned last time that I could put together a resource that I think would help you get some practice with these different ideas. So I went ahead and did that. So I've written some short targeted questions that I think are going to help improve your understanding for some of the basic skills we need in chapters 4, 5, and 6. Things like identifying acids and bases, assigning oxidation numbers. Let's see if we can get that automatic by just some really simple practice. So what I did within the system, the questions that are asked there, they're mastery based. If you get 3 in a row, you're done with it. Okay, that's how it's set up, getting 3 in a row. That could take you 40 seconds. It could take you 4 minutes. Depends how long it takes you to get 3 in a row. I think this is a really good use of your time, because if you know the idea, you can just check in real quick and move on. You don't have to work on it for 45 minutes. It's a really quick way to do a quick check-in and say, okay, do I know how to do this or not? This approach, it works if you have short, repeated practice. I'm going to ask the questions in different ways. You see multiple times in different ways, and it's going to become automatic. This is what cognitive science tells us for how we can, with simple repetition, learn things like this. So I think we can give it a try. So what I've done is I've gone to this website right here. My colleague has set this up for me. I write the questions. The website is called essentialskills.osu.edu. It's free for you to use. This is completely optional, but I think it can really help you. So what I've done is I've made these short check-in assignments, and I've got one every day next week. Okay, they're on things like assigning oxidation numbers, using the activity series, and you got nothing to lose. Okay, I know that these really quick, short check-ins, it's going to be really helpful as we pull together all the ideas from chapters 4, 5, and 6. There's a lot of different things. Give it a try. Okay, give it a try, and let's see how it goes. Like I said, I've got one set up so that you can log in. You can see the quick format. You got nothing to lose, and I think it can help a lot. Okay? So great job, everybody. As always, I appreciate your attention. I'll hang around if you got questions.
For expressing molarity,